Okay, on a piece of graph paper, graph y equals x squared from x equals 0 to x equals 4. I'd actually recommend making at least 3 different copies of this because you're going to do 3 different things with this. Okay, and so it should look like this. This is a parabola, and if you notice, it starts at x equals 0 and goes to x equals 4. So I'm going to scale this up to 16 because I know 4 squared is 16. So it kind of give me a feeling for how the x and the y-axis looks like. Okay, so if I blow up this picture a little bit, I'm going to estimate the area of this using rectangles. Bernard Riemann, a German mathematician, actually came up with this process. He realized that if you made a rectangle that used the lowest point here, and in this case, you would actually get a rectangle that had a height of 0, which would have no height. And he thought about using the highest point, which if you did that, you'd find the highest point in that region from 0 to 4, which would occur over here. And that rectangle was too big. There's no way that that rectangle estimated the area underneath that curve. So he played around with it and he realized that using the midpoint would give a approximation. So if I go halfway between 0 and 4, that would be at 2. And I use that to determine what the height of the rectangle is. You can see here that this rectangle here that's formed does a pretty good job of estimating. It's not perfect, mind you, but it's not bad either. If you notice this area here that's below the curve but above the rectangle closely matches this area here. It's not a perfect fit, but he found that it was a pretty good approximation. So he found the area of, this is called a midpoint Riemann sum. He used the middle of each of the intervals that he was looking at. So in this case, one rectangle from 0 to 4, the middle was 2. So if I plug that into the equation, remember the equation was y equals x squared, 2 squared, the height would be 4 times the width in this case would also be 4. And so that would give me an area of 16. So using one rectangle, give me an area of 16. We started to play around with it and realized, well, what if I were to split this up into 2 rectangles? How would that affect my results here? So he said, okay, so from 0 to 2 would be the first rectangle, and 2 to 4. And he realized he's going to find the midpoint of each of those. So he goes to the midpoint between 0 and 2, which was 1, and he goes up to where that hits the curve. He makes the area of that first rectangle be the height when 1 hits the curve. Then he looks at 2 to 4 and realizes, 3 is in the middle. So he goes up to where 3 hits the curve and says, aha, that's the height of the second rectangle. And actually it should be a little bit higher here. So I'm going to move up my rectangle here a little bit higher. And he said, okay, let's find the area of each of these rectangles, with the idea again that the area that the rectangles miss up here is approximately the same area as the area that the rectangle covers, but still above the curve. And likewise, this area approximates that area that misses there. So it's a pretty good approximation. So he looked at this and said, okay, the area of the first rectangle would have a width of 2 times, well, 1 squared, remember the equation is y equals x squared, would just be a height of 1. So this would have a height of 1. And the second rectangle would be, again, the height width would be 2, and the height would be 3 squared. And we'd add that up. Well, that became 2 plus 18, and he said, oh, that comes out to be 20. So this is a better estimate for the area of that rectangle, area underneath the curve, by using 2 rectangles. So I said, okay, well, 2 rectangles was good. 4 rectangles might even be better. So he decided, I'm going to split this up into 4 rectangles, each one having a width of 1. But remembering that the midpoint seemed to give him the best estimate. So he would find the middle of each of these intervals. So for example, between 1 and 2, the middle would actually occur at 1.5 squared. And that would be the height of that rectangle between 1 and 2. So between 0 and 1, he would pick 0.5 and go up to where he hit the curve, and he would make the height of that rectangle be 0.5, hitting the curve, 0.5 squared. And halfway between 2 and 3 would be 2.5, so where that hit the curve, that would be the height of his third rectangle. And between 3 and 4 would be 3.5, so again, where that hit the curve, that would be the area. And so he wanted to find the area of these 4 rectangles and add them up. Okay? So keeping this in mind, he knew the width of the first one was 1 times the height, which is the midpoint, 0.5. Remember the equation was y equals x squared, plus 1 times, so the second one was 1.5 squared, plus the third one had a width of 1 times, except now it was 2.5 squared, and then plus, for the final rectangle, 1 times the midpoint of that one was 3.5 squared. And he did some calculations, figured out that that totaled 21. And so that was even a better estimate, because once again, when he looked at those rectangles, he realized that the part that it missed, that was below the curve, below the rectangle, closely balanced out the part that was above the curve but below the rectangle. You can see here that these two sections are almost identical. They're not perfect, but they're certainly identical. And that section there is approximately there, and likewise that approximates those areas. So it turned out it was a pretty good estimate for that. And this is what he called midpoint Riemann Sums. It was a great way to estimate the area under the curve using rectangle. Okay, so let's see if we got this. By estimating the area under the curve, so remember that's the symbol for a definite integral, in this case from 2 to 6 of the equation x cubed dx, using midpoint Riemann sums with 8 intervals. So this is the notation that we use for a midpoint, telling me the number of intervals. So I need to sketch this curve, make this as big as I can. Y equals x cubed. Actually, in this region we look for, it looks a lot like y equals x squared. Okay? But we're going to look at it from x equals 2 to x equals 6. Okay? And we're going to split this up into 8 rectangles. So if you look here, the total width is 4. From 2 to 6 is 4. So if I split up into 8 rectangles, each interval actually has to be 0.5 units. So I'm going to split this up as close as I can. 1, 2, 3, 4, 5, 6, 7, 8 intervals. And I'm going to find the midpoint of each of those intervals. So the midpoint between 2 and 2.5, which is this one, is actually 2.25. And I'll go up to where that hit the curve, and it will be the height of that first rectangle. And the midpoint here would hit right there, and that area would be there. And I find the midpoint of each one of those intervals where it hits the curve, and that's the height of that rectangle. So again, I'm going to make 8 of these rectangles all the way up using the midpoint as the height. So I go up to where the midpoint hits the curve, and that's how tall I make the rectangle. A little bit easier to see with these rectangles over here to the right because of the nature of this curve. But you can see I'm using the midpoint, so I'll draw dotted lines here, to show where that hits the curve, and that's what the height of the rectangle is. And so I'm going to find the area of each one of those curves. So if I think about the process I did there, I looked at the interval from the first one, had a width of 0.5, which will actually be the width of every one of these rectangles. So I'm going to take advantage of that and say, okay, the middle rectangle, the very first rectangle, was actually 2.25, that was the midpoint, cubed, because that's the equation. And then I went to the second rectangle, which the midpoint there between 2.5 and 3 is 2.75 cubed. And then the next rectangle, the midpoint was between 3 and 3.5, so 3.25 cubed. And as you can see, there's a nice pattern here all the way to the last rectangle, which was between 5.5 and 6, so 5.75 cubed. And again, I'm going to multiply each one of those heights by the width of all the rectangles, 0.5. And so I got as an answer here, this total comes out to be, with my calculator, 319. And so then I know that the estimate for the area under the curve from 2 to 6 using midpoint Riemann sums is 319. Try again. 319. That is my estimate for the area under the curve. Okay, so Mr. Riemann, he decided to take a look at different types of sums. So let's take a look at the area under the curve from 0 to 3 for this equation, x minus 4 squared, which is this parabola, we're only looking at the region from 0 to 3. So this region between these two lines. I'm going to use an upper Riemann sum, which means that when I go to do each of the rectangles, I'm going to take the highest point within that region. So if I look at the region from 0 to 1, I find the highest point, which in this case is 0, and that's how tall I make my rectangle. So when I look at the region between 1 and 2, I find the highest point in that region, which will be right there, and that's how tall my rectangle is. And when I do the same thing between 2 and 3, the highest point would be there, and so that would be the area. These three rectangles would be in my estimate. Obviously, by looking at this would be an overestimate because the rectangles is definitely bigger than the area that I'm looking for underneath that curve, which is this area right there. So you can see there's parts of the rectangle that's above the curve that I'm including in my estimate. So this is going to be an overestimate. Okay? So let's take a look at a lower Riemann sum. So the same principle, we're going to look at it from 0 to 3. But now we're going to take the lowest point in each of the region. So when I look from 0 to 1, I go up to where the lowest point in the region, which is right there, and that would be the area of the first, or that would be the rectangle. Then from 1 to 2, the lowest point would be there, and from 2 to 3, the lowest point would be there. And so this rectangle, I would find the sum of these three rectangles, and this would definitely underestimate, because as you can see here, there's parts underneath the curve that my rectangles just don't get. So these are underestimates in this case. Okay, let's do the same thing. Same curve, if you notice, x minus 4 squared, but now we're looking at it from actually, let's change this from, instead of from 3 to 5, let's look at it from 4 to 6. So 4 is here, and 6 is here. Okay, so I'm going to find the area using the highest sum. Well, now notice here that when I come to between 4 and 5, the highest point is actually on the right side here. And so that's the height of that first rectangle. And between 5 and 6, the highest point is over here. And so there's, again, the area of the rectangle. And once again, there's the area below the rectangle that's not actually above the curve, so I can see that this is an overestimate. So upper sums seem to always overestimate. So let's take a look again at the region from 4 to 6, except use lower sums. Well, that one's a little bit tricky because when I do from 4 to 6, the lowest sum from 4 to 5 is actually 0. Again, actually a rectangle, it's 0. Between 5 and 6, the lowest point is here, right where 5 hits the curve. So this is a rectangle. This is definitely going to underestimate because there's parts underneath the curve that my rectangles just don't get. So lower sums always underestimate the area underneath the curve in whatever region that I might be looking for. So let's take a look at this function, okay? So let's try to estimate the area of this equation, 3 plus 2 sine x, from, let's say, 0 to 6. Remember, you have to write the dx. And let's use 6 subintervals, but let's take an upper sum. Okay, so remember, we're going to take the highest point. Well, if I look at 0 to 1, the highest point is where 1 hits the curve. So, okay, that's no problem. I can do that. When I go 1 to 2, this is where a problem occurs, because if you notice, the highest point is not actually at either 1 or 2. It's not on the edges, but the highest point is somewhere in the middle there. There's actually the highest point. So if I do an upper sum, that's the point that will help me determine the height of that rectangle, and it's not at one of the endpoints. Question is, where is it? Well, if you notice, this is a sine curve. So if you notice here, this is the starting point. Okay, it's been shifted up 3 units, so it's going to start at 3, and it's going to go up to 5, down to 1, etc. Well, it goes up to 5 at, if you remember your sine curves, at pi over 2. It comes back down to 3 at comes back down to this level. And then over here, this low point would actually be at 3 pi over 2. So I've got to remember a little bit about sine curves to actually find those maximums and minimums here. Okay, so let's go back to our problem. From 2 to 3, if we take the highest point, that's nice because that occurs where 2 hits the curve. No problem there. Between 3 and 4, again, no problem. The 3 becomes the highest point. Between 4 and 5, 4 is the highest point, so that'll be the height of that rectangle wherever 4 hits the curve. And between 5 and 6, notice that this is 6. It's on the right-hand side now. So for this particular rectangle, actually I have to use the right-hand endpoint. And so once I find the area of each of these 6 rectangles, I would use that to estimate the area here. And again, they should overestimate because you can see all the rectangles are bigger than the curve that I'm trying to estimate. Okay, so let's use lower sums with the same region from 0 to 6 times dx. But let's use lower sums now, okay? So when I do lower sums, I'm going to look for the lowest point within each of my regions. So from 0 to 1, if you notice, the lowest point occurs where 0 hits the curve. No problem. From 1 to 2, looks like, and that one's kind of tough, but it looks like 1, where 1 hits the curve, is a little bit lower than 2. And so that's the lowest point there. That's the height of that rectangle. Between 2 and 3, that's where 3 hits the curve. And 3 and 4, the lowest point is where 4 hits the curve. 4 and 5, there's the challenge. If you notice here, the lowest point is actually right there. And so it's where that hits the curve, that's going to be the height of that rectangle if it's a true low Riemann sum using lower sums. Between 5 and 6, that would be where 5 hits the curve, so it would be about there. So again, if you remember from my investigation of trig, or sine curves, this is at 3 pi over 2. So the lower sum would actually include the point where 3 pi over 2 hits that curve. So this is a little bit about Riemann sums. Basically are rectangles used to estimate the area of the curve. Remember, we've counted squares and we've used trapezoids. This is a third method using rectangles, and they're called Riemann sums due to the German mathematician, Mr. Riemann, who came up with this idea.